Have you ever wished for like a fast track to genuinely understand complex scientific topics? Getting those aha moments that make everything just click.
Yeah, that's exactly what we try to do here on the deep dive.
And today we're diving deep into electrophilic aromatic substitution.
That's right. We're pulling insights straight from Chapter 21 of Clayden, Greaves, and Warren's Organic Chemistry, the second edition. And we're not just covering the what, we really want to get into the why behind these reactions.
So by the end of this, you should have a much clearer kind of practical grasp of this core organic chemistry concept. We'll break down the mechanisms,
Well,
look at how different groups transform and like steer
in
reactions.
those subtle electronic and steric things dictating where stuff happens.
Exactly. And we'll even peek into some clever chemist strategies for building molecules precisely, touching on that whole idea of retrosynthetic analysis.
Okay, so let's start maybe by connecting back to something from Chapter 20, keto-enol tautomerism. Remember enols?
Yeah, this sort of electron-rich alter egos of ketones.
Yeah.
Nucleophilic.
Exactly. They've got electrons to share, looking for electron-poor partners. They're often fleeting, but super reactive when they're around.
Right, like with pentam 3,1 in heavy water, you see those alpha hydrogens swapping out for deuterium.
Yeah, that exchange is your smoking gun. It proves the enol form exists, even if briefly.
So how does phenol fit in, the HOH on a benzene ring?
Well, what's really cool and central to today is that phenol is essentially a very, very stable enol.
Stable because of the aromatic ring.
Precisely. That aromaticity locks the enol form in place. It's incredibly stable compared to a regular enol.
And you see that if you try to deuterate phenol, right, the deuterium goes onto the ortho and para positions 2, 4, and 6.
Exactly like other enols react.
Hmm.
But the key difference is it stays as that stable aromatic enol. So this really sets the stage. Aromatic compounds tend towards substitution, not addition, when they react with electrophiles.
Okay, so what about benzene itself, the classic aromatic compound?
Benzene, that unique structure, right? Planar hexagon, delocalized pi electrons.
Which means incredible aromatic stability, way more stable than you'd expect.
Absolutely. And you see that stability in its reactivity, or lack thereof.
Yeah.
Compared to cyclohexene, a simple alkene.
Alkenes love electrophilic addition, right? Bromine adds right across the double bond.
Yep. But benzene, under the same conditions, nothing. No reaction with bromine, no reaction with peroxy acids. It just sits there.
So it's pretty unreactive.
Very. But here's the twist. It can react with bromine, but you need a catalyst, like a Lewis acid, LCl3. A real heavy hitter.
And crucially, it undergoes substitution, not addition. Hydrogen gets replaced by bromine.
Exactly. Why? To preserve that precious aromaticity. Losing it is just too costly, energetically speaking.
So the big takeaway, benzene is stubborn, needs powerful electrophiles, usually cations, and always does substitution to stay aromatic.
You got it. That's the core idea.
Okay, so we know benzene prefers substitution. How does that actually happen mechanistically?
Well, the general mechanism is a fundamental two-step process. It's quite elegant, really.
Step 1.
Step 1. Attack. The pi electrons of the aromatic ring, acting as the nucleophile, reach out and attack the electrophile. This forms an intermediate antication.
Ah, the intermediate cation. And this is where things get interesting, right? It's delocalized.
Yes, the charge is spread out.
But it's not aromatic anymore.
Precisely. Because for that brief moment, one carbon atom becomes tetrahedral, sp3 hybridized. It breaks the continuous loop of pi electrons.
And losing that aromaticity is a big deal.
Huge. That's why forming this non-aromatic intermediate is the rate-determining step. It's the slowest, highest energy point in the reaction. The molecule really has to commit to lose that stability temporarily.
And we actually know this intermediate exists. It's not just theoretical.
Oh yeah, there's fantastic proof. Scientists managed to observe it directly using NMR spectroscopy, but at incredibly low temperatures, like minus 120 Celsius.
Wow.
And the NMR data confirmed exactly how the positive charges spread out, mostly on the ortho and para carbons relative to where the electrophile attacked. Seeing it directly really cements our understanding.
That's really cool. Okay, so let's look at some common examples of these reactions on benzene. Nitration, for instance, adding an SNO2 group.
Right. For nitration, you typically need a strong mix, concentrated nitric acid and concentrated sulfuric acid.
Why both?
Well, the sulfuric acid is actually the stronger acid here. It protonates the nitric acid.
Which then loses water.
Exactly. And that forms the real electrophile.
Mm-hmm.
The nitronium ion, NO2 plus Go. It's linear and very reactive. That's what the benzene attacks.
Got it. And sulfonation, adding SO2OH.
Similar idea, you need a strong sulfur source,
Hmm.
usually concentrated sulfuric acid, or even better, oleum, that's sulfuric acid with extra SO3 dissolved in it.
And the electrophile is SO3.
Essentially, yes,
Yeah.
or protonated SO3. And the product, the sulfonic acid, is itself a very strong acid.
Okay, now what about adding carbon chains? Friedel-Crafts alkylation.
Ah, Friedel-Crafts.
Yeah.
Named reaction, very useful,
Yeah.
but kind of tricky. Use an alkyl halide like propyl chloride
Hmm.
and a Lewis acid, typically aluminum trichloride, LCl3.
And the Lewis acid helps generate the electrophile.
Yeah, it helps pull off the halide, leaving you with a carbon with a positive charge. That's your electrophile.
Yeah.
But there are problems.
Right, I remember reading about this. Two big issues.
Two major ones, yeah. First, multiple substitution. The product, the alkyl benzene, is actually more reactive than the benzene you started with.
Oh, so it reacts again.
And again, it's hard to stop it at just one alkyl group unless you flood the reaction with a huge excess of benzene, which isn't always practical.
Okay, that's problem one. What's the second?
Rearrangements. This is a big one, mechanistically. The reaction only works cleanly if the carbocation electrophile is stable, like a tertiary or secondary one.
What happens with less stable ones, like primary?
They rearrange.
Yeah.
A hydrogen atom, or sometimes an alkyl group, can shift over to form a more stable carbocation. So if you start with, say, N-propyl chloride, hoping to get N-propylbenzene.
You might end up with isopropyl benzene instead, because the primary carbocation rearranges to a more stable secondary one.
Exactly. That hydride shift happens super fast, so it's really important for synthesis design. You might not get the product you expect.
Okay, so alkylation has its pitfalls. How do chemists get around adding alkyl groups more reliably?
There's a much cleaner alternative, Friedel-Crafts acylation, adding an acyl group, RCO.
So you make an aromatic ketone?
Yep. You'd use an acyl chloride, RCOCl, or an anhydride, again with a Lewis acid like LCl3. The electrophile this time is the acylium ion, RCO plus S.
And why is this better?
Several reasons, and they link nicely to synthetic strategy. First, the acylium ion is very stable because the positive charge is right next to the oxygen, which can share its lone pair. So no rearrangements.
That solves problem two. What about problem one, multiple substitution?
Solved too. The product, the aryl ketone, has that electron withdrawing carbonyl group. It actually deactivates the ring, making it less reactive than the starting benzene.
So the reaction just stops after one acylation?
Cleanly, beautifully, usually. One substitution, no rearrangements, much more predictable.
That's much better. But wait, you end up with a ketone. What if you wanted the straight alkyl chain, like that N-propyl group we couldn't get reliably before?
And here's the clever part, a key functional group transformation. You can take that ketone product from acylation and reduce the carbonyl group, CO, all the way down to a methylene group, CH2.
Reduce it? How?
Common methods are things like the Clemmensen reduction using zinc amalgam and HCl, or the Wolff-Kishner reduction. So you acylate first to get the ketone cleanly, then reduce.
So you get your unrearranged N-alkyl benzene indirectly, acylation, then reduction.
Precisely. It's a fantastic workaround. A really common strategy in synthesis, showing that kind of retrosynthetic thinking planning backwards from the target.
Very neat. Okay, let's shift gears a bit. How do groups already on the ring affect where the next substitution happens, the whole directing effect thing?
Right, this is crucial. Substituents dramatically influence both the rate of reaction and the position, the radioselectivity, of the next attack. We can broadly classify them.
Let's start with the activating ones. Groups that make the ring react faster than benzene itself.
Good place to start. These are typically groups that can donate electron density into the ring, making it more electron-rich and thus more attractive to electrophiles. Think OHAH in phenols, 8H2 in anilines, even simple opoar alkoxy groups or alkyl groups.
And they generally direct ortho and para.
Yes, they are ortho pair directors. Let's take phenols and anilines, NH2. They have lone pairs on the oxygen or nitrogen right next to the ring.
And those lone pairs can be donated in via resonance, right? Conjugation.
Exactly. That pumps electron density into the ring, especially at the ortho and para positions.
Yeah.
This makes the ring massively more reactive.
How much more reactive?
Hugely more. Phenol reacts with bromine water instantly, without a Lewis acid, often giving 2-paired 4 and 6-tribromophenol. You can't stop it at 1.
Whoa.
And anilines are even crazier. The rate increase compared to benzene can be like billions or even trillions of times faster. They're incredibly activated.
So that superreactivity can actually be a problem if you only want one substitution.
Definitely. Oversubstitution is common, which leads to another clever strategy. Sometimes you need to tame these groups.
Tame them? How?
Well, take an aniline, -NH2. It's too reactive. But if you convert it into an amide first, say by reacting it with acetyl chloride to make an acetanilide.
You reduce the nitrogen's ability to donate electrons
Yeah.
because the lone pair is also involved with the carbonyl group next door.
Precisely. The amides are much less activating, still ortho, para-directing, but now you can often get clean mono-substitution, usually favoring the para position due to sterics. Then afterwards, you just hydrolyze the amide back to the amide.
Another neat functional group manipulation to control reactivity.
Exactly. Synthesis is full of these tricks.
What about simple alkyl groups, like the methyl group in toluene? They also activate and direct orthopara, but not as strongly.
Correct. They are weakly activating. The effect there is called hyperconjugation or sigma conjugation. It's a weaker donation, involving the electrons in the CH sigma bonds adjacent to the ring interacting with the pi system.
And why orthopara directing?
If the electrophile attacks at the ortho or para position, one of the resonance structures of the intermediate cation puts a positive charge right on the carbon attached to the alkyl group. This is like a more substituted carbation, which is more stable. That stabilization isn't possible if attack is at the meta position.
Okay, makes sense. Now what about the opposite? Deactivating groups. Things that make the ring less reactive than benzene.
Right. These are electron withdrawing groups. Think nitro, NaCSNO2, carbonyl groups, NaCsCOR, nitryl CN2CN, trifluoromethyl, NaCsCF3, even positively charged groups like NaCnR3 plus NO.
And they pull electron density out of the ring.
Yes, either through conjugation, like nitro and carbonyl groups, which have double bonds that can accept electron density, or through strong inductive effects, like the very electronegative fluorines in NaCsCF3. This makes the whole ring electron poor and less attracted to electrophiles.
And these groups direct meta.
Generally, yes, they are metadirectors, and the reason is kind of the flip side of the activating groups. These groups withdraw electron density most strongly from the ortho and para positions. So those positions become particularly electron poor. The meta position is still deactivated compared to benzene, but it's the least bad place for an electrophile to attack.
Least bad.
Yeah, because if the attack happens at ortho or para, one of the resonance structures of the intermediate would place the positive charge right next to the electron withdrawing group, which is highly destabilizing. Attacking meta avoids this really unfavorable situation.
Ah, okay. So meta attack leads to the least unstable intermediate tataké.
You could put it that way. It's all relative instability. You see this clearly if you nitrate nitrobenzene, the second nitro group goes almost exclusively meta.
Right. Now, there's a weird category, isn't there? The halogens.
Ah, yes, the halogen paradox.
Right.
Fluorine, chlorine, bromine, iodine.
Oh.
Peculiar.
Peculiar how?
They're deactivated. They make the ring react slower than benzene, but they are ortho-para-directing.
Wait, how can they be both? Deactivating usually means meta-directing.
It seems contradictory, right? But it comes down to two opposing effects fighting each other.
A tug of war.
Sort of. First, halogens are highly electronegative. They pull electron density away from the ring through the sigma bond. That's a strong inductive effect. This withdrawal deactivates the whole ring. That's the dominant effect on the overall reaction rate.
Okay, so induction makes them deactivating. But why ortho, para-directing?
Because they also have lone pairs of electrons, just like oxygen or nitrogen. And these lone pairs can be donated into the ring through resonance or conjugation. This resonance donation preferentially increases electron density at the ortho and para positions.
But isn't that donation weaker than for O or N?
Much weaker. For chlorine, bromine, iodine, the orbital overlap isn't great because their orbitals are larger and diffuse compared to carbon's 2p orbitals. For fluorine, the overlap is better, but fluorine is so electronegative it holds onto its electrons tightly. So the inductive withdrawal wins out overall, making it deactivating. But the weak resonance donation is still strong enough to steer the electrophile to the ortho and para positions.
So induction controls rate, slow, resonance controls position, orthopara.
That's a good way to summarize it. And practically, even though the reaction is slower, you can often get good yields of orthopara substituted halobenzenes because that directing effect is still quite powerful, especially for para, due to sterics.
Fascinating balance of effects.
Huh.
Okay, let's move towards wrapping up with some more advanced strategies. What happens with multiple substituents?
Right. If you have two or more groups already on the ring, their directing effects can either work together, cooperate, or clash compete.
Cooperate how?
Like if you have a methyl group, OP directing, and a bromine, OP directing on the same ring, they might both point towards the same available positions.
And compete.
If you have, say, a strongly activating group like OH-OP and a deactivating group like OPNO2, meta, they'll be pointing to different spots.
So who wins in a competition?
Generally, the most powerful activating group dictates the position. Activating groups usually win over deactivating groups. Sterics also play a big role. If the position favored by electronics is too crowded, the reaction might go to a less crowded, electronically less favored spot.
Okay. And tying this back to synthesis, we already talked about the acylation reduction trick for alkyl groups.
Yes, a key strategy to overcome the limitations of direct alkylation, multiple substitutions and rearrangements. That acylation reduction sequence is a prime example of using functional group transformations strategically, thinking retrosynthetically.
Any other really key functional group transformations in this area?
Absolutely. The nitro group is a real workhorse in aromatic synthesis.
Why the nitro group?
Well, first, it's easy to put on via nitration. Second, it's a strong deactivator and a reliable metadirector. But the real power comes from what you can do with it afterwards.
It should.
You can easily reduce the nitro group, NO2, down to an amino group, NH2. Common ways are using tin and HCl or catalytic hydrogenation like H2 over palladium on carbon, PDC.
So you go from NO2 to NH2. Why is that so useful?
Think about the directing effects. You introduce a nitro group, it directs the next substitution meta. Then you reduce the nitro group to an amino group. What kind of director is an amino group?
Oh, it's a strong activator and ortho para-director.
Exactly. So this sequence nitration, then maybe another substitution directed meta by the nitro group, then reduction allows you to completely switch the directing influence. It opens up pathways to make molecules, particularly 1,4,0,3 desubstituted or 1,4,13-5 tree-substituted compounds with activating groups. That would be really difficult or impossible to make otherwise.
That's incredibly powerful. Introduce a meta-director, then flip it into an ortho para-director.
It's a cornerstone of aromatic synthesis strategy. Really showcases how understanding these transformations lets chemists build complex molecules with precision.
So we've really journeyed through the whole landscape here, haven't we? From benzene's basic reactivity
Through the mechanisms, the directing effects of all sorts of groups.
and into these clever strategies using functional group changes to control where reactions happen.
Hopefully, you now have a much deeper feel for the mechanistic reasoning, the power of these transformations, and just how chemists think about putting these molecules together.
Yeah, you've definitely equipped yourself with insights that go way beyond just memorizing reactions. It's a real shortcut to being genuinely well-informed on this fundamental chunk of organic chemistry.
Absolutely. It's a versatile and fascinating area.
We saw how reducing a nitro group totally changes the game synthetically, but it makes you wonder, what if you needed a group, say, a halogen or an OH in a really specific spot that you couldn't get to easily by direct substitution or even by that nitro trick?
That's a great question.
Could you, temporarily put other groups on the ring, use them to block positions or direct traffic, do your reaction, and then take those temporary groups off again, like using them as scaffolds?
That's exactly the kind of advanced thinking that drives synthetic innovation, using blocking groups or other temporary directing groups. It's like a carefully choreographed molecular dance.
Definitely something to keep in mind as you keep exploring the sheer ingenuity of organic synthesis.